All right, welcome back everybody. Today we're going to be breaking down a system design interview classic. We're going to be designing a rate limiter. Especially if you're new to system design, this is a fantastic place to start. It's a good problem to get familiar with. It's still incredibly popular at many of the top companies. It's asked a lot at Microsoft, for example, and many users recently have been reporting that it's being asked at OpenAI lately too. Now, for those of you who are new to the channel, I'm Evan. I'm a former Meta staff engineer and I'm the co-founder of Hello Interview. Hello Interview is a platform that helps people just like you prepare for upcoming software engineering interviews. And so if you haven't already, head over there, check it out. Now, if videos aren't your thing, we have detailed written write-ups on this problem, designing a rate limiter, as well as 26 others. You can see them all here. We also have foundational core concepts, deep dives into technologies, patterns that we think are important to know for system design, as well as plenty of content on DSA, behavioral, salary negotiation, interview guides. You got it, or you name it, we got it. Now, you can also try this problem yourself using our guided practice. And so you can come here, fill things out step by step, record your answer, get feedback, and this is going to be evaluating your design in real time for each question along the way, letting you know what you did well, and of course, the things that you can do in order to improve. So feel free to give that a go. The overwhelming majority of the content is free. Guided practice, everybody gets one for free. From then on, unfortunately, it's only for premium members. Hope you understand. All right, without further ado, let's get after it. Well, what even is a rate limiter? Chances are most of you are already familiar, but it's good for us to go over it so that we have a shared understanding before we design the system. Rate limiters control how many requests a client can make in a specific time frame. And so think about, you have a social media app, users are making requests in order to view news feeds, update posts, etc. And the rate limiter limits them to something like, for example, 100 requests per minute per user. And the whole point here is to protect our backend. It's to protect our services so that users can't come and abuse our system, spamming us with thousands of requests that ultimately might take down our system or make it unusable for other users. So that's what a rate limiter is. Now, before we jump into designing it, as we always do in these videos, we're going to outline the framework that we're going to follow both in this video and that I suggest that you follow in any of your real system design interviews. And so this is the Hello Interview delivery framework. We suggest you go step by step through these steps, starting first with your requirements. This is where we're going to define both the functional requirements or the features of the system, as well as the non-functional requirements or the qualities of the system. We're also going to outline some of the core entities. These are usually the nouns of your system. These are the rows that you're storing, or the tables, in your database, the things that are exchanged, the resources in your APIs. That's our core entities. And then we'll do either API or system interface. In the case of a rate limiter, which is like a back-end component, the client's not necessarily interacting with it directly, we're going to focus on the system interface. For some system design interviews, data flow makes sense. You could have it make sense here in design a rate limiter. I think we'll probably skip it and we'll go right to the high-level design, where the goal of the high-level design is to head over to the whiteboard, draw some boxes and arrows in order to satisfy those core functional requirements of the system. And so in other words, get a minimal design down early in your system design interview that's able to fulfill the basic features of the system. And then from there, we can move on to our deep dives, where we're going to layer on complexity by satisfying our non-functional requirements, such that our final design has everything it needs to be able to scale, be low latency, fault tolerance, all of those things that are really important. And so you'll watch me walk through this step by step. We'll do it together and we'll have some fun. For rate limiter specifically, let's jump right in then with our functional requirements. Again, functional requirements are the features of the system. Now, for user-facing applications, this is usually pretty straightforward. A user can write a post, a user can view a feed, whatever it may be. In the case of these backend components, it's sometimes a little bit more abstract, but I think it's still rather clear what needs to happen here. And so I'm going to do this in order of when a request comes in. Well, the first thing is that the application, the rate limiter here, needs to be able to identify users by something. In our case, maybe this is their ID, their IP, or even an API key. Right? So the most important thing is the rate limiter needs to know, who is this? Because I need to determine whether or not I should limit them based on how many requests they've already made. So that's step one. The second thing, and the most important thing, is that we need to be able to limit requests, right? We need to be able to limit requests, and these should be based on configurable rules. And so a configurable rule here might be that any user can only make 100 requests per minute, maybe even to a specific endpoint, right? And so we got to identify a user, and then we'll limit the requests that that user can make based on a set of configurable rules. And then the last thing is that we want to return proper error headers and status codes to the user. And so we don't want to be ambiguous here. We don't want to just return a failure of 500 to the user and them have no idea why. We want to tell them that they're being rate limited and maybe even give them some additional metadata so that they can deduce how they should move forward, what they should do next. So those are our functional requirements of our system. At our core, that's what we're designing. Now, before you move on to the non-functional requirements in your interview, my suggestion to you is always check in with your interviewer at this point and ask them about the scale of the system. Especially in the case of a rate limiter here, the scale is actually really interesting, and there's a lot of questions that you'd want to ask. And so I would ask my interviewer, what am I rate limiting? Is this a user-facing application like a Facebook or something? Is this some developer tooling? Is this rate limits between intra-microservices, maybe within a company? What am I rate limiting? And now when I ask this question, and as is most popular, you're typically going to be rate limiting some user-facing application like a social media app. And so we'll say that we have 100 million daily active users, and that means 1 million requests per second, okay? So we have 1 million requests per second, and we're gonna be rate limiting at that particular scale. Now, one other thing I actually want to note here is that when I ask this question, this is kind of funny. Candidates would always say to me, am I designing a back-end rate limiter, a server-side rate limiter, or a client-side rate limiter? And I'm going to be honest, this question was always a little bit confusing to me. It's like, of course we're designing a server-side rate limiter. A client-side rate limiter maybe doesn't provide nearly as much value in this case. It can obviously be spoofed. You can't trust the clients to limit themselves, right? And so I found out that candidates were always asking this because as I was doing some research to write up our breakdown of this problem, I saw that most other write-ups online start with that, is it server-side or client-side? And so, I don't know. Like I said, I think this is a little silly. It's going to be server-side. There are realistic use cases where client-side provides some added value, but I've almost never seen it asked in an interview. So a bit of a tangent or an aside from me. But yes, we're going to be doing a server-side rate limiter that is going to rate limit for an application that has 100 million daily active users and 1 million requests per second. And so with that, we can come to our non-functional requirements. And so non-functional requirements trip up a lot of candidates. What is a non-functional requirement, first of all? Well, if a functional requirement is the features of a system, right? What does the system need to be able to do? The non-functional is how does it need to be able to do it? And so this is where there's all those ILITY statements, right? This is where you're going to talk about scalability, low latency, durability, even security, fault tolerance. Now, if you head over to hellointerview.com under the delivery framework section, we list off all the things that you should consider in the non-functional requirement. But most importantly, you're not going to just write all of those things. Everything you write in the non-functional requirements, you're expected to address in your design. This is really crucial. And so you're going to want to call out the specific column ILITs, right, ILIs, that are directly relevant to this design, okay? And so pick out the ones that you think are most specific and most interesting, and we'll go forward with those. And so the first thing that you want to consider in your non-functional requirements is always CAP theorem. And so of course in CAP theorem, we have consistency, availability, and partition tolerance. Partition tolerance is a must. So your decision is always, should my system be strongly consistent, meaning should every single read be reading the latest write, or should we opt for high availability and thus eventual consistency is fine. Now, in our case, we're going to go for availability over consistency. You can think of this like if somebody was going to push a new rule to our system, would we rather that the rate limiter still works even if it's reading outdated rules for a bit while they're propagating? Or should we have the rate limiter basically go offline because we need to wait until all rules have propagated? That's one example of availability versus consistency. Clearly, we want to make sure that our rate limiter is still always just up and available and working because it's protecting our system. Now, the second thing that is uniquely interesting to a rate limiter is low latency. And so in any system design interview, a bad candidate, or I shouldn't say bad, but maybe a less good candidate would come in here and they would write this on the board, low latency. And I, as the interviewer, would say like, okay, yes, systems, it's good for a system to be have low latency, but what do you mean here? And now what a good candidate would do is they would be specific. And they would say we have low latency rate limit checks, and even better, we're going to aim for under 10 milliseconds. And so what they've done here is that they've both quantified and they've also qualified. So they said I want low latency in the case of a user making a request. We don't want to add additional latency to their request. And then we want to make sure that we add less than 10 milliseconds. And this is what they're going to try to design for. Now, of course, this is really important in a rate limiter because your rate limiter is adding additional time to any request from a user. That user requested something like a post. And we're going to take time to first check if they're allowed to view that post based on their rate limits. But we don't want to take a long time doing it. The user wants to see that post quickly, right? So low latency is important there. And then we sort of already implied that this was important when we talked about scale question above, but this system needs to be scalable. So scalability, right? So it needs to be scalable, and we want to scale again to quantify it to that 1 million requests per second. And so the goal of our functional and our non-functional requirements is to agree with our interviewer exactly on what we're building. We're basically setting up this contract with them, saying that for the rest of the interview, these are the things that I'm going to fulfill. And now I, as the candidate, can hold myself accountable. Because if I get to the end of the interview and I did all of these things well, I kind of did all 6 of these things here well, then I should feel confident leaving the interview, like I passed and I nailed it. And that's the general goal here. And so at this point, check in with your interviewer, ask them, is there anything I'm missing? Is there anything that you would change? Otherwise, I'd love to continue and move on to the next sections. The next sections for us is the core entities in the interface. Now, I'm going to admit, for these backend components, this is slightly less important, again, than a user-facing application, but they do form a basis, and they're not steps I would skip, but you can probably do them, frankly, in under a minute. And so let's do that. Let's kind of breeze through them. What are the core entities of a system like this? Well, the core entities that you have is a request. This is the request that's incoming. It's how you are going to determine who is making the request, right? And so like the who, I'm going to call them a client, but this is like your IP address. This is your user ID, the things that we talked about earlier, maybe your API key. Right? So you have a request come in, you have a client, and then you have rules, of course. These rules are the things like, 100 requests per user per second, right? So very simple. Those are the core entities of our system. They're good for getting us to wrap our head around what's going on here, and they lead us nicely to what would be either our API or a system interface. Now I'm going to go with system interface instead of API because we want to choose API when we're doing a user-facing application where users are calling an API. Users are not calling an API in this case. Users are calling an API of, for example, our social media app, right? Get posts, but it's us who are checking the rate limiter. And we're doing this via probably an RPC call or some internal call, which we can define as our system interface. And so you can do this however you want. I like to do it kind of as a function call. And really, it's just this one function that we're implemented. Is this request allowed, right, for this client ID in this rule? And we're going to return basically, did it pass? Is that allowed? True or false? We should also return, though, if we look back to our functional requirements, we wanted to return some interesting stuff here so the user knows what to do. And some of those interesting things might be, how many remaining requests the user may have if they do pass, as well as like maybe what time it resets. This would depend on what our algorithm is, which we'll get into in more detail later. But this is the thing that we're implementing. Some function that allows us to ask if a request passes or not. And so if we zoom out now, we should have a pretty good understanding. This was our setup. We have a good understanding now of what we want to build. We've done our requirements, our entities, and our interface. And it's time for us to head over to the whiteboard, do the really fun stuff, start drawing boxes and arrows, nail down our high-level design, and then our deep dives. As we get into our high-level design, the approach that we take here is actually really simple and methodical. You don't need to overthink this. You're just going to go one by one through your functional requirements in order to make sure that we can satisfy each of them. And so our first requirement is that the system should be able to identify clients by their user ID or IP address or API key and so on. But importantly, maybe before we can limit anyone, there's two key questions that we need to be able to answer. And so I'll write them over here so that we have them in mind. The first is, where should our rate limiter live in our architecture? Basically, where do we place it, right? And this is going to determine what information we can access and how it integrates with the rest of the system. And then the second question that we're going to need to be able to answer is, how should we identify clients? And so based on those user ID, IP address, API key, anything else, what's the right way to identify a user? And this assures that we, of course, apply the right rate limits to any given user. And so these two questions here, they're closely linked. Your placement choice is going to affect what client information you can easily access, and your identification strategy influences where the rate limiter makes the most sense to deploy. And so let's start with the first one here. Where should we place the rate limiter? That's the first thing that we're going to answer. And we have three main options. Now, the first option is pretty maybe obvious, and we can start with the simplest thing. Let me draw out, why is that so thick? Let me draw out what our basic system could look like. Right? So we're going to have some client, we're going to have a microservice architecture because we have some large system here, like our, what did we call it? Social media app, excuse me, hard to type and think. And so here's just our really basic setup. Okay, clients make requests to our social media app. It goes to our gateway. Our gateway then forwards that on and routes it to the appropriate microservice. That microservice does its thing and returns back to the client. Okay, so there's the basics of our social media app. And now we need to stick a rate limiter somewhere. When we talked about putting a rate limiter on the client, doesn't make as much sense. We alluded to that in the beginning. So we need some rate limiter back here in the backend or in server code. So where can we place it? The first option, I'll make it blue here, is that we can put our rate limiters directly inside each of our respective microservices. Right? Now, in this setup, it's just part of your application code. And so when a request comes in, the server is going to check its local memory for the current counts for any given user. It'll update them and then decide whether to allow or reject the request. Now, the good thing is this approach is extremely fast. Everything is happening in memory. There's no network calls. There's no external dependencies. But the downside, I think, is really obvious. There's no global picture. And so you can imagine that a user makes two requests where one hits microservice 1 and one hits microservice 2. And in each case, they both think that only one request has come in. However, of course, globally, the user has made two requests. And so the lack of coordination makes this a really poor option. And so what's the second thing we could do? Well, naturally, we could pull this out and maybe make this rate limiter its own service here, right? Make it global. And so now every time a request comes into one of these microservices, the first thing that they're going to do is check with the rate limiter and say, hey, am I allowed to process this request? Basically, is this under our limits? And if yes, they'll end up processing the request and sending the results back to the gateway or back to the client through the gateway. And so this is great in that it solves that global coordination problem that we were worried about. Wonderful. But it also is going to introduce some excess latency. And so now every single request that comes in is going to go from the gateway to a microservice. The microservice is then going to make a network call to a separate service, a separate server somewhere, which is your rate limiter, which is going to respond, and then it's going to do its thing and respond back to the user. And so admittedly, this is fairly minimal, but just keeping in mind, we had those tight latency requirements. And so we want to make sure this is as quick as possible. And this added network overhead probably isn't worth it. And so how can we keep that global picture, but maybe reduce the latency of that network overhead? And now the answer, and what is used in most production systems, is to actually just move the gateway over here to the edge. And so we can place it directly in either our API gateway or our load balancer, or whatever component sits at the front of our system, at the edge of our system. And now in this setup, every single incoming request is going to hit our rate limiter first. And so right before we determine where to route this request to, we'll just say, hey, can we even service this request based on our given limits, right? And so for those of you maybe who like analogies, you can think of this placement of our rate limiter like a bouncer at the club, I think is the kind of silly but canonical example here, right? And so troublemakers are going to get turned away at the door, not after they're already made it inside and started to cause problems, like was the case in the previous approach, right? Now, this still has some limitations. The first is around scale, but that's fine. We'll talk to that as we get to our non-functional requirements. But more importantly, this limits the amount of context that we have. And so when we had the rate limiter in our application code, we in theory have context to everything about our system. And so if you want to make complex rate limiting rules, like rate limit somebody differently based on whether they're a premium user or something, that was easy to do. But now as we sit at the edge, we only have information that came in via the HTTP request itself. So the headers, the URL, the IP address, and any basic authentication tokens that are present in the actual request. We can't see that deeper business logic that might exist inside of our application code with access to some persistent storage like a database. And so this is fine. To give that example again, maybe we want to do the premium user thing. Premium users get 10x higher rate limits. It's still doable. We just need to make sure that the fact that a user is a premium user is encoded in the request. This is typically via the JWT token, which is going to be in the headers. And so anything the client send over should say, in this case via the JWT, that they're a premium user. So we have that context, we do our rate limiting, and then our microservices can focus only on servicing requests. They don't need to know about anything about how we rate limit or whether we rate limit. Now we want to answer that second question that we outlined, and that's how should we identify clients? Well, to be honest, we've kind of been talking about this the whole time. We even put it directly in our functional requirement with user ID, IP, API key, etc. But this is something that you're going to want to bring up and talk to your interviewer about. It's basically what makes a client unique. And those are the three main options: the user ID, the IP address, or the API key. But this is a perfect time to ask your interviewer some questions. And I would ask them, are all of our users authenticated? Is this a developer API that's going to require an API key, etc.? These are the sorts of things that you might want to ask. But in practice, and this would maybe be the most impressive answer to give your interviewer, is that we're probably going to want a combination. Maybe authenticated users get higher rate limits than anonymous IP addresses. Or as we talked about earlier, premium users may get even more. This is a reflection of your understanding of real world systems, and you're not going to enforce just a global limit, but probably have layers of multiple rules. And so you might have Alice can make 1,000 requests per second, any given IP address can make 100 requests per second, an API can handle 50,000 requests per second, whatever it may be. So we're going to be able to identify all of these things, apply them to different rules, and they're going to be identified, as we've talked about, just via the request, usually from the request headers. Now we can move on to our second functional requirement, where it's the system should limit requests based on configurable rules. And so this is where we get to the heart of rate limiting, and that is the algorithm that decides whether we should allow or reject any given request. Now, importantly, in system design interviews, this being the algorithm, isn't actually usually the main focus of the interview, unlike is the case in low-level design interviews. Now, you're still going to want to be able to acknowledge that you know the different options, that you can weigh the different trade-offs and explain and justify your choice, but you likely won't need to implement it, not even in pseudocode. So, with that said, there are many different rate limiting algorithms, but I think there's 4 that are worth you knowing. And so let's start with the simplest, and we'll work our way up. The simplest is what's known as the fixed window counter. And it's incredibly straightforward. Users get n requests per window. So for example, 100 requests a minute. And for each user, we're going to maintain a counter that resets at the start of each window. If the counter exceeds the limit during that window, we reject the request. And so I probably should have pasted this in a moment ago, but here is the diagram that we have in the article to work with here. And so these are each window interval. Requests come in this simple diagram. It looks like we have 3 requests per window until we start to reject. You get to your 4th request, it passes that threshold, and we end up ultimately rejecting it. Now, the upside of this is that it's really, really trivial to implement. You just need a hash table that can map your client IDs to counter and window start pairs. And so that hash table might, let's see if I can copy that better. That hash table might look something like this, right? Where you just have Alice at 12, she had 100 requests. At 12:01, she had 5 requests, Bob, Charlie, Dave, Eve, and Frank, respectively. So really, really, really easy to implement. But the downside is what we end up calling the boundary effect. And so a user can make 100 requests at 12:01 and 59 seconds, and then at 12:02, they can make 100 more requests, because they went on either side of the boundary here. And thus they ended up in effect making 200 requests in just 2 seconds, right? Which isn't great. The other thing is that there's the option for starvation. And so if you made your 100 requests at 12:01 and 1 seconds, now you have to wait 59 seconds until you can make any requests at all, which, depending on your needs, might also be a problem. Now, the second approach is called the sliding window log. Why am I blue? Sliding window log. And it basically just smooths out the issues that we had with the fixed winner counter. And so let me get this new drawing in here for you. All right. And as the name implies, we have the sliding window. And so as requests come in, we keep track of this rolling window over the last minute, and we just say something like we can only have 100 requests in the last rolling minute, right? Now, this eliminates the boundary effects and the burst problem from the fixed window counter that we had over here because it tracks the exact time of each request, which is going to give you that perfect accuracy. However, the downside here is that this is typically implemented with a heap or a deck. And this is going to require a ton more memory. And so if you have a ton of users, this is going to be tons more memory. It's more memory per users, and it's going to need a bunch more instances, and it's going to be more expensive. So that's the potential downside here. So the third algorithm addresses the memory issues that we have with the sliding window log by using what we call a sliding window counter. And it's basically the sliding window log, but with some mild optimization so that we don't have to keep every single timestamp that comes in something like a heap, right? We can be clever and instead just keep 2 counters. One for the previous fixed window and one for the current window we're in right now. And now the key is that we estimate what a true sliding window would look like by weighing these 2 fixed windows based on how far we are into the current window. And so let me just show you an example. I have an example written here that I can paste in. And so imagine that the previous window from 1 minute to 1 minute, 1 second had 8 requests. And now we're 42 seconds or 70% into our second window. And so far we have 6 requests. Well, should we accept the next request? Right? Well, here's the math. Given that we're 70% through the minute, we can take our current requests as well as 30% of the last window, right? 30% of the last window. This is us estimating how many more should we get in the remaining 30% of the window, right? And this is going to estimate that we're at 8.4. Now, if our limit was 10, we could say 8.4 is less than 10, and thus we should pass. Right? And the great thing here is that this gives us much better accuracy than those fixed windows, but we only need to use 2 integers per user. We don't need to keep a whole heap per user, right? So downside, it's an approximation. It's not perfect. It's not going to be perfectly evenly, it's an approximation, and it assumes that requests are pretty perfectly evenly spread across each of these windows, which aren't necessarily the case. But if you can handle this approximation, this is a pretty decent option. Now, the last option, and the one that is arguably most popular, and the one that we're probably going to go with, is what's called the token bucket. So let me paste in my cute little drawing here. Hopefully you guys like this one, right? But you can think of it as each client has their own bucket that holds a certain number of tokens. And these number of tokens in the bucket, they're the burst capacity, okay? And now, at the same time, tokens are being added to the bucket at a steady rate. And these are called the refill rate. And every time a request comes in, we consume 1 token. If there are no tokens available, then the request is rejected. Right? So that sounds a little confusing, but it accomplishes 2 things really nicely. The size of your bucket is how you handle bursts, those bursts that we talked about earlier. And so if your bucket starts with 100, then I can handle a burst of 100 at any given moment, right? And then my refill rate, this is like the steady number of requests per minute or per time that I can handle. So if your refill rate was, 60 a minute, then we're going to add 1 new token every minute. And that means that our steady rate is going to be run 1 request a minute, right? And each time a request comes in, we pull it out. And so an example, a bucket holds, like I just said, 100 tokens. This is going to allow bursts of up to 100. If the refill rate was 10 tokens per minute, this is a steady rate of 10 requests a minute. And then clients can make 100 requests immediately, but then they'll need to wait for the bucket to refill, and they'll be at that slower rate. And so this is really great because it handles that sustained load by our refill rate and the temporary bursts by our bucket capacity. It's also shockingly simple to implement. You just need to track the tokens and the last refill time for every given client. So again, just 2 numbers. But the challenge is choosing obviously your right bucket size and your refill rate and how you handle cold starts and things like this. But it's a pretty elegant algorithm, and it's the one that we're going to choose for our design here.
So we understand how the token bucket algorithm works conceptually. But where and how do we actually store each user's bucket, right? How would we actually implement this? Each bucket needs to track 2 pieces of data, the current token count and the last refill timestamp. And the state needs to be shared across all the different instances of the API gateway. And so importantly, in a real production system, you're going to have multiple of these gateways. And so they need to share some global state. If they don't, then we run into the same problem that we talked about earlier when we stored specific rate limiters inside of each microservice respectively. And so what we can do is we can pull the rate limiter state out into an in-memory cache, something like Redis. And so these token counts and the last refill rate, all of that state can be shared here in Redis, such that even though we have multiple gateways, they'll all still going to read that same shared state. And so what actually is going to happen here? Well, maybe let's write this out for extreme clarity. First, a request is going to come in, of course. The second thing is that the gateway is going to fetch the token and last, typing while you guys all watch is always difficult, from Redis. Okay, and so in Redis, we can use what's called an HMGet. And so what an HMGet is, it allows you to get the values of multiple keys. And so we can say for Alice's bucket, we want the tokens and the last refill. Right? So see that command there, that's pretty great. We're just saying in one command, give me her current tokens and the last time that it was refilled. Cool. And then what we can do then is calculate based on when her last refill time was, how many tokens we need to add to her bucket. And so this is really simple. If Alice's bucket was last updated 30 seconds ago and her refill rate is 1 token every second, then the gateway is going to need to add 30 tokens to her current count, right? So maybe her current count was 20, the last refill rate was 30 seconds ago, we refill at 1 every second. So now the count is 50, right? So the next step here is update counts based on rate and last refill. Great, right? And then of course we're going to respond pass or fail based on if token after the refill, or excuse me, if kind of tokens after that refill is greater than 0. Are there any tokens in the bucket? Given what was in the bucket and how much should have been refilled since the last time that we checked this, are there greater than 0 tokens? If yes, then we can pass. Right? And then the fifth thing is to update the bucket status. And so this is where we will write back and update the token count to whatever that new token count is, update whatever update the last refill time to whatever the current timestamp is, right? So make sure that everything gets updated. That's the general flow. But importantly, hopefully this makes sense so far, there's a race condition, right? So I want you to imagine the following. Let me try to illustrate this. I have gateway A and I have gateway B. And Alice sends in 2 requests. One request hits A, one request hits B. They both go and read Redis for our token counts. Right? So they both go and say, what is my current token and my current last refill rate? Well, in both cases, they're going to read the same value. That value might be 1. Right? It comes back as 1. They both check. Maybe the last time we checked was a second ago. There have been no more tokens added. So they both read, they both say, okay, it's 1, that's greater than 0, we're going to accept. They both accept, and they both go right to Redis. Maybe this one writes a nanosecond before than this one, so this one overwrites the previous. Right? The important bit here is that the race condition is that we have this read after write problem. You can have the read from gateway A, then the read from gateway B, then the write from A, then the write from B. When those two things, the read and the write for each, have to happen atomically, right? And so the key is that these things, the one read from Redis and the 2 write back to Redis, has to be atomic. In a Postgres database or anything, this is done, of course, like via transactions with locking as well. In the case of Redis, it supports atomic transactions and it's single-threaded, which actually makes this a little bit easier. And it's something called Lua scripting. Lua scripting. And so I'm not going to go into too much detail here, but the general essence is that you can have all of these Redis commands, this hmget, the hset, in order to update the token counts, all via a single a single Redis Lua script, right? And then it'll go over the wire, it'll do the read and write all in one instance, and then return to you whether or not you should pass or not. And that all happens atomically. Then you don't have the race condition. It's basically like one does everything, and the other one waits until the other one is completely finished. Okay. Hopefully that makes sense. Okay, fantastic. So what have we done here? Coming back, we have now covered our first and our second functional requirement. All that's left is that we need to return proper error headers and status codes. And this is pretty straightforward. This is the easiest one here. I guess there is one decision that we want to make. And that one decision is that if we've exceeded a rate limit, what do? Do we reject immediately? Or do we queue it and wait and try to handle it later? This might seem obvious to many of you listening, and I've almost been alluding to this throughout. We're going to take the approach of what's called fail fast. And so if we exceed the limit, we're immediately going to send a failure back to the user. We're not going to queue it. In a system like this, queuing doesn't make any sense. If a user is asking for posts to view their posts, we queue it. They're waiting and waiting and waiting. They think something is broken anyway. They hit the button again to try to view their post again. Now we just have a bunch of requests sitting in our queue, and a backlog is growing. It becomes an even larger issue. And so there are niche cases where queuing makes sense, like for batch processing systems that can afford to wait. This is usually like intra-service communication. But for the interactive fast API like we have here, this fast failure, fail fast is the most common and the right choice. But how do we make sure then that our response is actually helpful? Well, the first thing that's worth noting that you're definitely going to want to know for an interview is that the HTTP status code that you're going to send on failure is a 429. 429 means too many requests, and it is the standard HTTP status code that is used for exactly this. When you want to rate limit somebody because they've had too many requests, you send back a 429. But there's some additional headers that are best practice that you want to send back to the client as well. Forgive me, I'm going to copy and paste it so you guys don't have to watch me fumble through typing anymore. Let me put them here. Right? So you want to send back probably 3 additional things. The X rate limit. This is the rate limit ceiling for the requests. Right? So if you can have 100 per minute, that's what you're going to put in here. The X rate limit remaining, this is the number of requests left in the current window. Of course, the notion of a current window will depend on your algorithm, so this can get a little bit funky, but you want to give them some notion of where they are. And then the rate limit reset. When is this going to reset? There's other ones like retry after is a common one that's added here too. Retry after. This will say, try again in 60 seconds. Now, most importantly, in your interview, you should know 429. I think interviewers expect you to know the response code is 429. But when it comes to like memorizing rate limit remaining, rate limit reset, retry after, don't stress it. You do not need to memorize these. In an interview, I would say something like the following. I would say, I'm going to make sure that I return a 429 status code with the appropriate headers, like some headers that can let the user know when they can try again or how many are remaining. Right? Pretty clear.
So we have our high-level design in place. We're feeling pretty good about it. We chose our algorithm. The basics are all working here. But now we need to go back to our delivery framework, and next up is our deep dives. And so this is where we go one by one through our non-functional requirements in order to expand upon our design to make sure that each of those non-functional requirements are satisfied. And then we can really feel good about what we put here. So I'm going to move some of this around just so that we have a bit more space. You guys will have this whiteboard linked below in the description for anybody that wants to reference it. Now I'm going to go a little bit out of order when we talk about our non-functional requirements. I'm actually going to work with scalability first. We want 1 million requests per second. And if you come back to our current design, it should be relatively clear why this won't scale to 1 million requests per second. And the reason is that we have just this single Redis instance. And so Redis can handle, somewhere on the order of, depending on the hardware, maybe 100,000 requests per second or operations per second. And that's a tenth of what we need to be able to support. But of course, if you remember what we actually need to do, we need to do an HM get and we need to do an HM set. We need to do both of those things for every call. So that's 2 operations. So maybe we can even say that with what we have, we can support 50K requests per second. And what we need to do then is we need to shard. And sharding, of course, is the strategy for which we can introduce more instances and shard the data across those instances. Okay, so you can take a large collection of data and then shard the keys of that data across multiple Redis instances. To put that far more clearly, Alice might be on Redis instance 1, but Bob's bucket might be on Redis instance 2. Okay, and so let me demonstrate that here by adding a bunch of those. We need 1 million requests per second. And so if we have 1 million divided by our 50K, well, this is 20. So we'll need at least 20 of these. Maybe we want to tell the interviewer that we want a little bit of room for overhead, so we'd have more than that. But now the question becomes, how do we shard? And this is important because the gateway always needs to know that I just got Alice's request, so I need to look in whichever Redis instance has Alice's bucket. If we just checked a random bucket, then we might not have Alice. And if we just replicated all the data to each of these buckets, well, we're in the same problem, right? All of the buckets have all of the data. And so we might run into issues of the actual amount of size that we're storing. These are in memory. So 64 gigabytes, maybe you go up to 100 and something gigabytes, right? But we can't store an infinite amount of data. So how do we want to shard? Well, you obviously want to shard based on whatever your client ID is. In this case, the user ID or the IP address or the API key. And you can use something like consistent hashing. I'll try to remember to put a link to our consistent hashing video somewhere on the screen now, so you can click on it if you're not familiar with consistent hashing. But in reality, what you'd probably end up doing if you are using Redis is that you would use what's called Redis cluster. And Redis cluster manages this kind of sharding for you. And it does this not actually using consistent hashing, it uses what's called hash slots. And so it has something like 60,000 hash slots that it distributes across each of these different Redis nodes. It handles the distribution into which hash slot any given user is in and thus which Redis node they're in. And then it will all be handled within what is called, as I said, Redis cluster. And so that would be an easy way to handle this, but the main conceptual thing for you to know in your interview is that we need multiple instances and thus we need to shard, right? Easy enough. Now, the next thing that we should talk about then, again, I'm going out of order, is the availability over consistency. And so how do we ensure that we have high availability and that we're also fault tolerant, right? And so if we come back here, well, what happens if Redis fails? What happens if any of these particular instances fail? If Alice's bucket is on this particular node and this node fails, well, then now Alice can't be rate limited, okay? And so the first thing that we might want to talk about is, well, what happens if that did happen? And then we can talk about how we want to prevent it. And so if that did happen, then we have two options. Option 1 is fail open and option 2 is fail close. This is common terminology when you discuss rate limiters. Fail open means our rate limiter is down and thus every single request should get through. Fail close is the opposite. Our rate limiter is down and now no requests should get through. And so you'll probably want to talk to your interviewer in order to understand the requirements of this particular system. We've understood that we're designing a rate limiter for some sort of a social network. And so in the case of failing open, we would be kind of no longer protecting all of the services that we were here to protect. And it may introduce a bunch of issues downstream. Like there was a rate limiter here for a reason. And it's probably because there are limits to how many times we can read from our database or our cache or how many times we can compute something algorithmically within any of our microservices given the limitations that we have in CPU or even GPU respectively. Right? So in our case, if we were to fail open, we would basically say, just go for it, send all requests, and then these microservices one by one might be back here and might die and go offline. We might have this cascading set of failures that are even worse. On the other hand, if we fail close, then now our site is down and you're going to have a bunch of users who are upset, who are reporting, oh no, Facebook, Instagram, whatever we're designing this rate limit for is down, and that's maybe not good either. There's no right or wrong answer. I think typically what you're going to do here is you're going to fail close. The responsibility of the rate limiter is to protect the backend services to some degree, and thus if it's down, then it needs to take what is the strictest protection mechanism possible, and that is to reject everything. I will note that there's oftentimes in real production systems more sophisticated things that you would do here than just this binary fail, open, or close. Like you can keep some state in the gateway. The gateways themselves, of course, have memory. And so maybe you have like a single counter in order to do a fixed window counter, such that if these fell off, then you could fall back to maybe the fixed window counter using the memory within the gateway. And then it doesn't matter that we don't have the coordination between multiple gateway instances, as we talked before, because it's like this is just a temporary thing while Redis gets back up. It's better than nothing. It's better than failing open or failing closed. At least we still have some rate limiting capacity. So if any of these go down, that's what we would do. But more importantly, how do we make sure that A, I guess none of these go down, and two, that if they do go down, we get them up as quickly as possible. And the key, as is the case with most distributed systems, is replicas. Right, so we can configure a replication factor such that each one of our Redis shards, each one of our nodes here, have one or even two replicas, such that all data that gets written to them also then gets propagated to its replica. And if one of these were to go down, bink, then its replica would be promoted, and all of the reads would then come to the replica instead. Now, similarly, like we talked about with sharding, Redis cluster actually supports this for you. And so with Redis cluster, sorry about that noise in the background, there's some construction going on. I'll see if I can get that out in post. But similar to with sharding, with Redis cluster, you can configure a number of these backups. And these backups use async replication. So it's not perfect. We're opting for high availability instead of consistency. That's the trade-off here. So a write happens. If this fails, before the write gets written here asynchronously, then yeah, we'll be missing some data there, but it's not the end of the world. Like now we think Alice is at 99 requests instead of 100. Right? She got one extra request off of us, but no big deal. So the key to the high availability and the fault tolerance is sharding and read replicas. Okay, and Redis cluster can satisfy both of those. Now let's talk about the low latency rate limit checks. So how do we make sure that we're sub 10 millisecond latency? Well, every single check now is going to require this network round trip to Redis, and this is going to add latency to every single request, of course. And so Redis operations are typically sub millisecond, but the network overhead here can be, in some cases, several milliseconds per request, right? And then the fact that we have these larger requests might make them even slightly longer. And so the most important optimization that you can do right here is what's called connection pooling. And this is so instead of establishing a new TCP connection to Redis for each rate limit check, your API gateway is going to maintain a pool of persistent connections here. And this is going to eliminate that TCP handshake overhead, which can sometimes be 20 to even 50 milliseconds depending on your network distance. Okay, and we're just going to reuse those same TCP connections. Now, this is interesting to say in your interview, and you should talk to your interviewer about kind of TCP connection pooling. But note that most Redis clients will handle connection pooling automatically for you. I don't know a single one that doesn't. It would be crazy if it doesn't. But you may need to tune the pool size based on your request volume and the Redis response time. So this is a good thing to know. But in your interviewer, you should probably tell your interviewer that you understand that this connection pooling will likely be handled for you by whatever Redis client you use. The other additional interesting thing to talk about here when it comes to latency is the geographic distribution. And so what you would want to do is you want to make sure that your rate limiter and even your gateway are as close to your users as possible. And so if you have users in Tokyo, then maybe you have a gateway that is somewhere in Asia or somewhere in Japan. And subsequently, Redis, your Redis instance, is located or co-located with your gateway, ideally even in the same data center, as close as possible, right? These two servers might even be right next to each other to try to minimize that latency as much as humanly possible. At this point, we should be feeling pretty good. We have satisfied all of our functional requirements. We've satisfied all of our non-functional requirements. But there's one more thing I want to talk to you all about that's pretty common as it comes up in interviews. And I want to make sure that you guys are as well prepared as possible. And that's how do we handle dynamic rule configurations? And so right now we've just sort of assumed that there were static rules. Like maybe when the gateway was deployed, it had some basic rules which said the token refill rate and, you know, the token count in the bucket. And so we always just use these rates, these hard-coded rates. And if you ever wanted to change it, you would need to redeploy your gateway. Now you could also store them in Redis, you could do a bunch of different things, but we've assumed thus far that they are static. And so what happens if they were configurable, as is the case in most production systems? And sometimes you want to have different rules for different users and different types of things like we talked about with Premium and otherwise. And so how would you handle that? Well, let's talk through a couple of options. The first, maybe silly option would be that your system has a database. This is a database I'm sure that your microservices are talking to. And it could store something like whatever your rules are, which premium users, last refill rate, etc. Right? And your gateway could maybe just periodically pull. And so maybe every 20 seconds it pulls like this. Okay, that's an option. Now, it's not an ideal option because we have this 20 seconds delay here, or 10 seconds delay, or even a 5-second delay, and you could make it 1 second, but now you're just burning unnecessary gateway CPU that should be doing other things in order to do this constant pulling, right? So that's not great. You can also, of course, just pull from Redis. Like you definitely don't need the database. In each of these Redis shards have that key value with all of the rules, and periodically pull in the rules. Maybe even each time you check a rate limit request, check the actual rules, right? Look up the key that has the rules and find out if the rules have changed at all. This is just going to add additional operations to every single check, and it's going to increase your latency unnecessarily, considering rules probably aren't going to change that often. So it's an option, but again, probably not the best option. The best option is that you can use a pushed base configuration. And actually, Zookeeper, a bit outdated nowadays, I must admit, or etcd, right? These are options here, the latter of which kind of being a bit more in vogue than the old school Zookeeper, but I think conceptually the same general thing. And so what these are is that these are designed in order to maintain this distributed configuration management. And so the rules can be stored here. And not only can the gateway, when it comes online, ask for the rules and then store those rules, importantly, in memory. And it's going to keep those rules in memory so it doesn't have to do a network check every time. It has those rules there. But it can also subscribe to watch for changes. And so what it can do is that then opens up a persistent TCP connection such that anytime a rule changes in Zookeeper that this gateway wants to know about, it gets pushed over that open TCP connection, and then the gateway can update its rules in memory. And so this saves all of the issues solves all of the issues with the previous two approaches, which is that we don't have any additional latency or network requests because the rules are kept here, and we don't have to pull. Zookeeper is just going to push when it's ready.
There you have it, folks. At this point, we've satisfied our high-level design and our deep dives, and we have a pretty comprehensive design of a distributed rate limiter. Now, if you are a mid-level candidate, then the expectation is that you're going to have more 80% breadth and 20% depth. And so I would expect from you as an interviewer, I would expect that you understand the different rate limiting algorithms and you make a choice and justify that choice appropriately. You might not be able to code them or know them perfectly in depth, but conceptually you should understand them. You should understand that the rate limiter would make the most sense existing on the edge of our system, and you should propose something in order to share state globally, whether that's Redis, Memcache, or otherwise, and be able to justify why you're adding it. Beyond there, you should be able to answer my questions as I probe as an interviewer. When I point out that there's limitations with a single Redis instance, for example, or when I ask questions about what happens when something goes down, you should be able to problem solve and arrive at reasonable answers given my probing and me leading you to the answers. Now, for senior candidates, on the other hand, I expect you to be much more proactive. You're identifying those issues proactively. You're telling me, the interviewer, that you recognize that a single Redis node isn't going to cut it here. Here's the math that proves why, and here's how many shards I'm going to need and what I'm going to shard on. Right? You're going to be more proactive in those ways, talking to me about fault tolerance, but all the things that could potentially go wrong if the system gets overwhelmed, failing open, failing closed, etc. And then as a staff candidate, realistically, this question is not asked nearly as often of staff candidates. It's a little bit maybe kind of on the easier or medium side maybe. But if you are asked this as a Steph candidate, I'm expecting a lot more depth. I'm expecting you to proactively lead through just about everything that we've talked about here maybe, but then you'll also guide me towards conversations of things that you know really well. Maybe you have deep experience of Redis cluster, and you can tell me about times where you had to, or you accidentally or incorrectly managed the connection pool size. You made mistakes there and why it's important that it needs to be a particular size. Or you proactively recognize the race condition and you explain to me how Lua scripting is going to work in order to solve the race condition, right? That's a little bit more of an advanced concept. So that's how you would break it down, mid-level, senior, and staff, respectively. Let's see, anything else that I want to say here? I will put this diagram in the description, so if you want it, go check it out there. I'll be posting more videos, plenty more videos on this YouTube channel will be coming. And maybe the last thing, we're so close to 100,000 subscribers at time of recording this. If you liked it, please like, subscribe, leave a comment down below. I'll answer those. And as always, best of luck with your upcoming interview. You guys are going to do great. Take care.